Good evening, ladies and gentlemen. My name is Shambretov Nikita. I'm gonna be the host of today's event. Nice to meet you at the annual scientific conference held by the English department of the Physics Department of Moscow State University. It was founded more than 10 years ago by the senior lecturer Amalia Bardina, supported by the head of the English department, Irina Kovalenko. It has been regularly held twice a year since then. The aim of such conference has always been to provide the students of the physical department with an incredible opportunity of developing English-speaking skills alongside with acquiring public performance skills. The given conference is dedicated to the memory of Dima Bushin. Okay, there are 15 speakers on the agenda, and the first speaker is Anvar Hafizov. Let us greet him.
Let's start. Greetings, ladies and gentlemen. Again, my name is Hafizov Anvar. I'm a computer vision engineer in Federal State Research Center Crystallography and Photonics, Russian Academy of Science. And today I'm going to tell about machine learning in case of microtomography, its application, training, data acquisition. To start with, I want to introduce the X-ray computed tomography in a nutshell. As you know, it's a powerful physical technique and it's non-destructive that could be used for obtaining inner structural materials, human bodies, bodies of animals, and so forth. So it has various applications, starting with medical issues and ending with petrol science, digital rock physics, and etc. As for me, I'm mostly interested in investigation of porous samples using this method, due to it is widely used in petrol science. So here we can see the diamond example of a porous structure. It could be a piece of rock. When you scan it using CT, you obtain a 3D image of this piece of rock, a numerical image. And here, here we can see the 2D scan, vertical scan of this 3D image. As you can see, it's a scope of pixels that are encoding using continuous numbers ranging from -infinite to +infinite. And if you want to do some calculation with that, like so you have to calculate some properties of it, permeability of liquid, for example, or strength properties, you have to deal with them. You have to remove the noise from it. And also you have to binarize it. It means that you must decide which pixels are corresponding to pores and which ones are corresponding to zeros. So you have to move to discrete space where the image is encoded in zeros and ones. So here in this slide, we can see two types of binarized images. I can ask you a question. Which one do you prefer, on the right hand or on the left hand?
The right one.
The right one.
Yeah, of course. The right one is quite better, I think. It's because the low noise impact. On the left hand, you can see the high noise occurrences, and in my opinion, it will drastically influence some algorithms, the likes of if you want to calculate some pore size distributions or maybe a specific surface area. So it's quite harmful. So there are lots of binarization techniques, but all of them could be subdivided into two classes. The first one is the classical approach. So here we have to firstly filtrate our image from noise. So by this way, we do some mathematical transform and we suppress the noise. Then we are doing thresholding binarization. It means that we take a particular number as a threshold, and for each pixels, we compare its brightness with this threshold. If the brightness or the pixel is below this threshold, we can say that it corresponds to pore. And if the pixel brightness is above this threshold, we can say that it corresponds to the material. So here we can see the example of its binarization, and it's quite good. But it's not in all cases. It is sometimes robust, but sometimes not. So it depends on particular situation. It has some drawbacks, the likes of computational power. It's quite demanding. The next one and the second is the modern-based methods based on machine learning. So here we also take an experimental image and we put it into a machine learning model. It's like a black box in that kind. Then we, as a result, obtain a binarized experimental image. So what is machine learning model? Let's assume that we have a function that takes features of an experimental image and somehow multiplies it by parameters called weights and do some other mathematical transform. And as a result, it gives some features of our experimental binarized image. So the question is, what is this function or sequence of functions? It could be a simple way, logistic regression. By the way, we have published a work considering logistic regression in the field of binarization. And in comparison with all techniques, it worked perfectly. The next question is how to teach this model. So teaching means that we give some examples of experimental rough image and their qualitative binarizations. But where can we? This means that we give to our model a training data set, and the function fits so the answer for the questions that we give is quite perfect. The next question is, where can we get a good training data set? The first is the simple answer. So we can just hire lots of people and to force them to make it manually. So they will have to manually decide whether there are pores or materials, but it's quite boring and actually we don't have lots of money to do that. So we would like to do the second and more universal approach. We would like to make an algorithm of its generation automatically. And here we can see the general pipeline of its generation. So initially we have an experimental image from which we calculate some characteristics. First characteristics are considered pore structure itself. It could be porosity, characteristic pore size. The next one is the noise characteristics, because as we remember, as the experimental image, we can have lots of noise. Then we take our characteristics of pore structure and generate some artificial image that will kind of similar to the experimental one. This image called phantom because it's artificial, it's not existed. Then we apply to this binary phantom, by the way, it's binary, it's also made from ones and zeros, some noise. And we move from discrete space to a continuous space. And the noise pattern depends on noise characteristics that we have extracted in the previous step. By this way, we obtain a trained pair. And performing this algorithm again and again, we can obtain a training data set with lots of pairs. So then our machine learning approach looks like this. We take our experimental image, from which we extract some parameters and create data set, using which we train our machine learning model. Machine learning model is deployed for binderize our experimental image. So as you can see, there is three main steps to our research. The first one is the fast porosity estimation of the experimental images. And this work has already been done. And you can see scanning this QR code, the work that was published in the conference. The next one is determination of pore characteristic size. And now we have three ideas how to deal with that. And probably it will be published in ICMV, International Conference of Machine Vision, that will hold in Rome, Italy in 2021. And the last question is the most tricky one, noise pattern simulation. And now we have only guesses and don't have any ideas how to implement that. Probably some Markov chains or another probabilistic theories will be deployed. So to sum up, I gave you a general view of tomography, its application, and problems that could occur. Two main methods of image processing were described, the classical approach and the modern one. Three steps of training data generation were described. The calculation of porosity that has already been solved, characteristical pore length that is about to solve, and the noise pattern extraction that is in progress. By the way, it's a little bit advert. If you want to join our work, you can write me on WhatsApp using this number. And now we are collaborating with two institutes. It's mine institute, Institute of Crystallography, and our partners, Institute of Microelectronics and High Purity Materials located in Chernogolovka. So thank you for your attention. Now I'm ready for your questions.
I have a question. Good evening, my name is Ivan. I am bachelor student of robotics in my University in Petersburg. And my question is, what are the advantages of machine learning methods over classical ones?
As I think, it's probably speed of performing of the algorithm. And also it could be quite robust in some cases. So when you use classical approach, you have to filtrate image, as I said. And when you do filtration, there are various filters and some of them are parametric. So you do have to know about these filters a lot, and you do have to know about these parameters, how to select the more appropriate ones. But when you use machine learning, it's unbiased and it's quite easy to implement that.
Thank you.
Thank you for your question as well.
Thank you, Embar. Let us thank him. And our next speaker is Kirill Murashov. Let us greet him.
Good evening.
Mm-hmm.
Mm-hmm. Yeah, so Kirill, you're welcome.
Yeah, can you see my screen?
Yes.
Yes, we can.
And we can see you.
That's great.
Mm-hmm.
Good evening, ladies and gentlemen. My name is Kirill Murashov. I'm a first-year master student of Moscow State University, physics department. My specialization is neutron physics and physics of nanosystems. And today I'll present to you a report on the topic of my scientific work, investigation of the structure of the carbon nucleus in an excited state with energy of 15.11 MeV. And I would like to start with the outline of my report. I'll start with the main goals of my work. Then I will continue with the theoretical basis of my work. After that, I will shed some light on the analysis of elastic scattering in the input and output channels, and the results of the analysis of the data on the reaction which is presented on the slide right here. And at the end, I will summarize the main results. So, dear colleagues, let me begin with the main purpose of my work. The goal of this work is to master the methodology for calculating the cross-section for elastic scattering and direct transfer of nucleons in order to study the properties of the 12 carbon nucleus in an excited state of energy 15.11 MeV based on the analysis of new experimental data. In this work, I checked whether the 12 carbon nucleus in excited state of 15.11 MeV has spin parity 1 plus. I also tested the assumption of the presence of a proton halo in the 12 carbon nucleus in this excited state. And now let's move on to the description of the scattering theory. So systematic optical model potentials are very useful in many fields of nuclear physics. They are needed for analysis that rely on the distorted wave-borne approximation for extracting nuclear structure information. The central assumption of that model is that the complicated interaction between an ascendant particle and a nucleus can be represented by a complex mean field potential, which divides the reaction flux into a part covering shape, elastic scattering, and a part describing all competing non-elastic channels. The following formula, number 2, gives the parameterization of the optical potential U as a function of R, which is the distance between a projectile nucleus and a target nucleus. Here in this formula, V, WV, and WS are the depths of the real potentials and the volume and surface imaginary potentials, respectively. And F is the Woods-Saxon form factor. So now I would like to draw your attention to the description of the calculation of the reaction cross-section. The computer code DVAC4 calculates the scattering and reaction observables for binary nuclear reaction using the distorted wave-borne approximation, or DWBA. The calculations are performed using zero-range interaction. The computer code calculates a transition amplitude for the reaction of the form according to the formula 5. The differential cross-section for the reaction may now be expressed in terms of the transition amplitude T by the formulas 6 and 7. And now, ladies and gentlemen, let's look at analysis of the data in the input and output channels. And this work, I investigated elastic scattering in the input channel of the reaction at free helium energy of 25 MeV. I took as a basis the global potential from paper Global Free Helium Optical Model, potential below 270 MeV. I checked this global potential on the available experimental data taken from the X4 BNL database. Since the angular distribution calculated with the global potential described the experimental data as unsatisfactorily, where were selected energy independent parameters that give a better description of the experimental data. Here you can see the figure. Dashed line indicate angular distribution based on a global parameters, solid line based on optimal parameters, and dots and experiment. As for analyzing the data in the output channel, The global potential from the article optical model potential for deuteron elastic scattering with 1p shell nuclei was taken as the basis for describing the scattering in the output channel. I have tested this global potential on available experimental data taken from the database. Uh, Based on the values of the parameters of the global potential, I tried to find the optimal parameters, but no significant improvement in the description of the data was obtained. Uh, when selecting the parameters, it was taken into account that these parameters should give integral characteristics and a cross section close to the global potential. So here, as you can see in the figure, the dashed line indicates the angular distribution based on global parameters. The solid line indicates the calculated optimal parameters, and the dots indicate the experiment. Uh, so finally, I would like to provide you with an analysis of the nuclear reaction and structure of the carbon nucleus. In this part of work, I analyzed experimental data for the reaction. The calculated angular distribution is shown in the figure in comparison with experimental data. The red line corresponds to the DWBA calculations, and the dots indicate the experiment. Here, the parameters of the model one particle potential of the Wood-Saxon form are selected for the best description of the main peak at the front angles. The main contribution is made by the direct transfer reaction. A good description of the main peak of the angular distribution confirms that for 12 carbon in an excited state with energy of 15.11 MeV, the spin parity value is 1 plus. So here, using the above formulas, I estimated the root mean square radius of the 12 carbon nucleus in the 1 plus state, which turned out to be 2.68 femtometers. For comparison, the root mean square radius of the 12 carbon nucleus in the ground state is estimated at 2.31 femtometers. So, ladies and gentlemen, today I have enlarged your knowledge in the subject of direct nuclear reactions. As a conclusion, I will summarize the main results of the work. As a result of the work, it was obtained confirmation of spin parity 1 plus for the 12 carbon nucleus in an excited state with energy of 15.11 MeV. An estimate of the root mean square radius of the 12 carbon nucleus in the excited state of 15.11 MeV, which turned out to be increased by 16% in comparison with the ground state. The form of the one particle wave function of the transmitted proton will with a more extended asymptotic, and the data obtained indicate the presence of a proton halo in the 12 carbon nucleus in an excited state of 15.11 MeV. So, dear colleagues, thank you for your attention. I'm happy to answer your question if you have any.
Yes, I have one question.
Yeah.
You showed the graph a couple of slides ago when you talked about the radius of the nucleus. How does this graph relate to the radius of the nucleus?
This graph shows the dependence of the form factor F on the distance R, distance of the nucleon from the center of nucleus. So if we calculate the square of the modulus of the form factor, we get the probability of finding a nucleon at a distance R from the center of the nucleus. Therefore, this graph shows that probability distribution of nucleons in the nucleus. So the root mean square radius can be obtained by integrating along the curve in this graph.
Thank you. Now it's clear.
Thank you for your question.
Let us thank Kirill for his interesting presentation. So our next speaker is Mikhailov Pavel. Let us greet him.
Can you see my presentation? Can you hear me? Everything
Yes.
okay?
Yes, we can.
Great. Good afternoon, ladies and gentlemen. My name is Mikhailov Pavel. I'm a third-year undergraduate student of Lomonosov Moscow State University, Faculty of Physics. I specialize in physics of semiconductors and cryo-electronics. Today, I want to tell you about physics of superfluids and quantum vortices appearing in them. Here you can see the structure of my report. Firstly, I would like to explain several important concepts from physics of superfluids. Secondly, I will shed some light on quantum vortices and superfluids. Furthermore, I will show you some real footage of quantum vortices. After that, I will show you how nanomechanical resonators can help us to explore quantum vortices. And at last, I will make a conclusion. Dear colleagues, let's start. First of all, I would like to tell you about what superfluidity is. Superfluidity is a property of a liquid with zero viscosity that therefore flows without any loss of kinetic energy, flows through very small pores, and obeys in only its own inertia. In the right part of the slide, you can see the picture of a cup with superfluid helium-4. Please pay attention to the bottom of the cup. You can see a droplet. The superfluid helium-4 flows along the walls of the cup due to its zero viscosity. The thin film of helium that covers the walls is called rolling film, and it has thickness approximately of 30 nanometers. This situation is represented in the left picture. So, how does it appear so that normal helium to become superfluid? As we cool, for example, helium-4 down to temperatures about 2 or 3 Kelvin, we observe the broad wavelengths corresponding to thermal motion of atoms to be of the same order as interatomic distances. That is why, in this temperature range, the properties of liquid helium are associated with quantum phenomena. In this sense, one can speak of superfluid helium as a quantum liquid at very low temperatures. And moreover, helium remains liquid until the temperatures of absolute zero instead of turning to solid state as it is predicted in theory. It is crucial to understand why helium-4 doesn't experience any energy dissipation. The thing is that helium-4 is a boson particle with zero spin. It means that there can be arbitrary number of particles in the same energetic state. Due to discreteness of energy levels of helium-4, the energy of interatomic interactions may be not enough for any energy transport between atoms at very low temperatures. And that's why helium doesn't experience any energy dissipation and flows without friction. As for fermion particles, they can form boson particles by pairing with themselves in the process similar to electron pairing in superconductivity, so-called Cooper pairing. This is the way how the third helium becomes superfluid, but at much lower temperatures than helium-4 does. And here I would like to make a little stop in my presentation and ask you if you have any questions about the material covered.
Yes, Pavel, I have a question. During your presentation, you have mentioned only helium-3 and helium-4 as superfluids. Are there any other superfluids?
Actually, there are other superfluids, starting from, for example, cold gases of fermion particles and getting up to even solid state. But it is crucial to understand that helium-4 has quite soft conditions to become superfluid. It needs only 2.17 Kelvin and 1 atmosphere of pressure instead of, for example, 15 nanokelvins for lithium gas, thermal gas, or 2.6 millikelvin and 34 atmospheres, as I remember, for the third helium. And this is the brilliance of first helium.
Okay, thank you.
Now, if there are no questions, I want to tell you about what a quantum vortex is. Imagine a normal liquid, water for example, rotating in a centrifuge. As water has non-zero viscosity, it will be accelerated by the rotating walls. And we observe such radial velocity distribution as shown in the picture number 1. But will the distribution be the same for a superfluid liquid? As we already know, superfluid liquid has zero viscosity and it won't be accelerated by rotating wall. And here we need to turn to quantization of circulation for a quantum vortex in superfluid liquid. This is expressed in the first equation. This equation shows us that any vortex that appears in a superfluid will have only discrete values of circulation. This is the key point that differs usual vortices and quantum ones. In the simplest case, we derive radial distribution of velocity for a quantum vortex in superfluid liquid as shown in the picture number 2 and in the bottom of the slide. You see two absolutely different radial distributions. In the left part of the slide, you can see a simulation of a tangle of quantum vortices. In the right part of the slide, you can see the real footage of quantum vortices. This footage was made by using micron-sized solid particles of hydrogen. These particles were put to high temperature helium, and the system was cooled down to make helium superfluid. As quantum vortices form, hydrogen particles line up along their vortex lines, and we can see such a picture. Dear colleagues, let's change the topic a bit and speak about my research direction. Nowadays, I'm actively studying fabrication and development of non-mechanical resonators and their further application to quantum vortices exploration. These nanoscale devices appear to be extremely sensitive to different physical quantities, such as mass, pressure, or force. That is why they are able to measure the response of superfluid helium-4 and, in particular, the interaction of quantum vortices. Interaction of quantum vortices. Since the mechanisms of interaction of quantum vortices and nanowires are not completely understood, this research direction is of high scientific interest for understanding the formation of quantum vortices and their interaction with other bodies. So, how does a typical setup for probing superfluid helium looks like? Here on the slide, you can see the real experimental setup for probing superfluid helium-4 with non-mechanical resonator. Non-mechanical resonator is included into the high frequency electrical circuit and is connected to VNA circuit analyzer with two -40 decibel low noise amplifiers. The device was put in helium and the system was cooled down to millikelvin temperatures. Magnetic field perpendicular to the plate of the device was turned on. Using the circuit analyzer, we can measure the response of superfluid helium to the excitations of non-mechanical resonator, and that's how we measure or detect quantum vortices. Dear colleagues, my presentation has come to the end. Today, I've told you about one of the most important and most interesting directions in modern physics. I wish that during my talk, I've expanded your knowledge in the sphere of quantum liquids and quantum vortices appearing in them. Thank you for your attention. If you have any questions, I'll be glad to answer all of them.
Yes, I have a question. Where theory of superfluids can be applied?
Actually, there are lots of applications of the theory, but one of the most fundamental of them is the theory of the superfluid vacuum theory. The theory is an approach in theoretical physics where the fundamental physical vacuum of space, for example, is viewed as a superfluid. The ultimate goal of this theory, as I remember, is creating a complete theory that would unify quantum mechanics and gravity. I think so, yes.
It's interesting. Thank you.
Thank you, Pavel, for your great presentation. So our next speaker is Vladimir Kuratsev. Let us greet him.
Can you see my presentation?
Yes, we can.
Okay. Good evening, ladies and gentlemen. My name is Vladimir Kuratsev, and I'm a third-year undergraduate student of Moscow State University, Physics Department. I specialize in biophysics. What I would like to do today is to present extremely interesting science observations to you. Here is the structure of my talk. Firstly, I start with introduction. Then I will tell you something about platelet hemostasis, especially about activation, aggregation, adhesion, and its dependence on shear rate. The most important part of my speech will be about my oven thrombus model at the initial stages of platelet hemostasis. Finally, I will try to make a conclusion. I would be happy to answer any questions at the end of my talk. Go to our next slide. Nowadays, the first place in the number of deaths has been occupied by diseases that lead to a violation of the hemostasis process. For example, ischemic heart disease, stroke, and road injuries in some cases. What do you think about the most common reason of such diseases? I'm ready to listen to your opinions.
Okay, Vladimir. Maybe the most common reason of such diseases is violations in attachments to the site of damage, so the blood doesn't stop.
It's interesting. The son of Emperor Nicholas II had similar problems, but this is not the main reason for such statistics. Anyone else have any suggestions?
Yeah, it seems to me that in some cases, blood clot blocks the blood flow. Is it right?
Exactly. The most common reason is uncontrollable growing of the thrombus that leads to the blockage of the vessel. It's a noticeably big problem for modern medicine. Moreover, without deep understanding of hemostasis processes, this problem is unsolvable. That will bring us to our next point. What is hemostasis in general? Hemostasis is a set of biochemical reactions and physical interactions in our body with the main goal to stop bleeding. It can be solved with two mechanisms: platelet hemostasis, which is creation of blood clot, and plasma hemostasis, which is transformation of blood to more viscous state with difficult cascade of biochemical reactions. Plasma hemostasis is extremely complicated, important step, and nowadays we know enough to explain all biochemical reactions which provide making blood as jelly. Unfortunately, we don't have enough time to explain it. And in this work, we will concentrate on platelet hemostasis. Today we know that to start platelet hemostasis, platelets must be activated by some molecules, for example, specific proteins, ADP, thrombin, thromboxane, and others. It provides thrombus growth and stability. When platelet is activated, it becomes capable to connect with the place of injury and with other platelets with specific interactions. These processes are known as adhesion and aggregation. Based on the results of numerous studies, at least 3 different mechanisms of platelet aggregation can be distinguished, with a relative contribution of each mechanism depending on the prevalent shear rate conditions. Under conditions when the flow rate is less than for about 1,000 reverse seconds, integrin on the surface of free-flowing platelets can meet fibrinogen adsorbed on the surface of platelet. This adhesive interaction can occur independently of the interaction of the Willebrand factor and GPIB receptor. Although even at such rates, the later adhesive interaction may play a certain role. at shear rates for about 1,000 to 10,000 reverse seconds. The processes initiating aggregation are quite different, including additional receptors, ligands, and membrane bindings. At these shear rates, platelet-platelet interactions gradually become more dependent on the Willebrand factor. At speeds of about 10,000 reverse seconds, the aggregation mechanism doesn't require platelet activation or the adhesive function of integrin, and is exclusively mediated by adhesive bonds of von Willebrand factor and GPIB receptor. With such a high shear rate, a characteristic feature of the aggregation process is a pronounced deformation of the platelet membrane, and it's very interesting. Platelet attachment occurs due to the binding of special receptors on the membrane of platelets, for example, glycoproteins and integrin, with certain proteins on the surface of the injury. The fact is that von Willebrand factor molecules immediately bind to the collagen exposed from the damaged endothelium, and platelets from the stream bind to this complex, and then to collagen using the already named receptors on the membrane. This process triggers signaling within platelets, which leads to both the activation of integrins and to the onset of thrombus formation. The main purpose of my work is to analyze the concentration dynamics of primary platelet activators by constructing a model of the process of platelet hemostasis. Uses the example of an ADP molecule. A microvessel with typical arterial shear rates up to 1,000 reverse second with 100 micrometers in length and 30 micrometers in diameter is considered. Platelets are represented as ideal ellipses. Below the injury site is an area that is impermeable to the flow, which is subendothelial matrix with the same dimensions as the vessel. Two dense platelet granules ejected due to activation slightly above and below one of the platelets can secrete ADP into the bloodstream. The calculations were carried out by varying the following parameters: the location of the dense granule, the number of platelets in the aggregate, and the possibility of diffusion through the injury. To simulate the blood flow in a venous vessel, the stationary Navier-Stokes equation is solved. The problem of convection diffusion is also solved for dissolved ADP molecules secreted by dense granules. As you can see in the picture, here are differences both in the absolute values of the concentration and in the kinetics of the process, depending on the various parameters of the system. The possibility of diffusion of substances into the subendothelial matrix leads to a significant change in the kinetics of elution of substances and requires consideration in exciting models of thrombus formation. In conclusion, I would like to say that the hemostasis system has a complex structure that requires detailed consideration to solve the problem of violation in its functioning, leading to death. Thank you for your patience and attention. If you have any questions, I will try to answer them.
I have a question for you. What does ensure the stability of thrombus?
It's an incredibly good question. Thank you. Recent studies have shown that a complex of signaling and adhesion receptors present on the surface of platelet serves to regulate the stability of the resulting aggregates. Central to maintaining thrombus stability is maintaining a high degree of integrin adhesion bond involvement. ADP plays a key role in maintaining the necessary integrin activation for the development of stable platelet-platelet adhesion contacts in the thrombus.
Thank you very much. Now it's more clear.
Thank you, Vladimir. Let us greet him. Let us thank him.
Sorry, I have one question, one more
sorry.
question
Okay.
for Vladimir. Yeah, good evening. My name is Lisa Liva, and I'm a third-year undergraduate student of Moscow State University, Faculty of Economics. So, Vladimir, why does the organism still need coagulation hemostasis if there is platelet hemostasis?
Interesting question. During platelet hemostasis, gaps between the cells are formed, through which the blood plasma can leak out. To eliminate them, coagulation hemostasis is present in the organisms. The main purpose of which is to transform this blood into a gel that is not able to freely seep through the injury. I think that's all.
Thank you. Now it's clear for me.
Questions? If no, let's continue. Again, thank you, Vladimir, for his work. In my opinion, it was breathtaking. So the next to speak is Georgy Bykov. Let us greet him.
Give me just a second to show you my screen. Can you see it clearly?
Yeah.
Okay, so I will start. Good evening, ladies and gentlemen. My name is Georgy Bykov. I'm a third-year undergraduate student of physics department, and I specialize in biophysics. My scientific interests are chemical and physical processes occurring in human blood and ways to regulate them. Today, I will talk about circulatory system and describe what am I doing to develop this sphere of science. Here is the structure of my talk. Firstly, I will briefly consider the circulatory system. Secondly, I will talk about differences between veins and arteries. Next, we will touch on the system of protection of the circulatory system. After that, I will dwell on the main points of my model. Further, I will tell you the main results. And finally, I will make a conclusion. Ladies and gentlemen, let's start, shall we? So first of all, let me remind you that our circulatory system consists of two circulatory circles. When passing through a small circle of blood circulation, venous blood is saturated with oxygen and is sent through the four-chamber heart to the organs of the large circle of blood circulation. Blood moves through the veins and arteries. Arteries have thick elastic walls because blood pressure in them is high, up to 120 millimeters hydroarcum above atmosphere pressure in aorta, the biggest artery in our body. Through arteries, blood flows to organs, and veins in their turn take blood away from organs straight to the heart. Pressures in them are much smaller, so their walls are thin. In addition, the blood flow in veins pulsates at frequency corresponding to the heart rate. The blood may even stop in veins, but it will not flow in other direction due to venous walls present in veins to prevent backflow. This system is built by nature to transport nutrients, metabolic products, hormones, and many other substances necessary for the functioning of our body. The importance of the system is obvious, so it is logical that there should be appropriate mechanisms to regulate and protect it, and they exist. The blood clotting system is a complex network of biochemical reactions, the purpose of which is to stop bleeding when the integrity of vascular bed is violated, caused by both external damage and various internal microtraumas that constantly occur in our body. As a result of the work of the clotting system, a blood clot is being formed at the site of injury, preventing further blood loss. It consists mainly of platelets, red blood cells, and fibrin, which is formed from fibrinogen under the action of the enzyme thrombin and then polymerizes. Disorders in blood clot formations are deadly. They lead to bleedings, for example, in hemophilia, to excessive clotting and blockage of blood vessels throughout the body, thrombosis, or to a combination of them. The fight against clotting disorders is complicated by the high complexity of this process. It involves dozens of proteins interacting in hundreds of reactions with each other, with blood cells and vascular wall. And this interaction occurs against the background of the diffusion of participants of the reaction and their transport by the bloodstream. A key obstacle to the development of more advanced methods of diagnosis and therapy of blood clotting is a lack of understanding of its regulation. In this complex network of reactions, only one, where polymerization of fibrin is directly needed to the transition of blood plasma to a gel-like state. The rest of the cascade, with its complex mechanisms, dozens of factors, inhibitors, positive and negative feedbacks, performs a purely regulatory role. Figuring out why the blood clotting system is so complex and what role each of its components plays can lead to qualitative progress in our ability to manage it. Now that the subject of the study is clear and the task is set, I'm ready to discuss a simple model of blood vessel, which I built considering it without complicated chemical reactions. Fundamentally, models of cardiovascular system can be divided into three groups according to their scale. The first is global models that describe the overall health of the whole person using heart rate, total blood volume, and blood pressure. The second group, models of branching vascular network. Such models are used to study the transport of oxygen, the phenomena associated with heterogeneity of blood flow, and the influences of violation of the structure of vascular networks on the development of pathologies. The third group, models of separate vessel. With their help, the processes of blood clotting inside of the vessel are studied. My model belongs to the third group. I once again do not consider chemical processes occurring in blood because it is shown that contribution of the von Willebrand calculation factor to a formation of a hemostatic plaque depends on the shear forces which I unfold this protein molecule. I believe that this factor plays a key role in the process of hemostasis, so I set out to predict the shear rates in wounds. It seems to be necessary to define some terms here. Von Willebrand factor, which is a protein which provides movement of platelets to the area of damaged vessel, is one of the main blood clotting factors. And shear rate, which is a derivative of the velocity in the direction perpendicular to the shear direction. In this model, I considered two geometries of weights. The first one is needed to check if the initial values we use are in correspondence with biological norm. Another one is needed to study injuries. At first scheme on the left, we see healthy vein. It is simply a pipe of circular cross-section with blood flowing inside of it. The second one on the right is also a pipe of a circular cross-section and a round hole in the side of it. We can call it wound. Blood is flowing in the vein and out of it through a wound intra-extracellular fluid, which initially is dormant. In the model, it is assumed that a single phase, that blood is a single phase incompressible Newtonian fluid, which means that we consider only fluid itself. There is no structures as platelets in it. Also, fluid doesn't change its density, an obvious Newtonian law of viscous friction in its flow. Results obtained from the modeling say that the maximum value of shear rate near the wound was more than million inverse seconds. In now existing books about arteries and arterial blood flows, it is mentioned that the values of the shear rate more than 5,000 inverse seconds are thought to be abnormally elevated if we talk about blood in intact vessels. So in conclusion, I can tell that the above calculations give us reason to believe that large values of those velocities are normal physiological values. This reasonable assumption may prove to be a crucial feature which distinguishes hemostasis from thrombosis. Thank you very much for your attention. In case there are any questions, I am ready to answer them.
Yes, I have a question. So, good evening, everybody. My name is Vasilevskaya Varvara, and I'm a third-year student of Moscow State University, Faculty of Fundamental Medicine. So, as I heard, you mentioned disorders of blood clot formation, and one of them was combination of hemophilia and thrombus formation. It's very unusual, so can you give an example, please?
Of course, one of examples is disseminated intravascular coagulation syndrome. Symptoms may include chest pain, shortness of breath, leg pain, problems speaking, or problems moving parts of the body. Relatively common causes include sepsis, surgery, myotrauma, and cancer.
It's very interesting. Thank you.
You're welcome.
If there is no question anymore, so thank you, Georgi, for your great presentation. And the next speaker is Sergei Pankratov. Let us greet him. Sergei?
Yes, just 1 minute, sorry. Can you see my presentation?
Yes, now we can.
Yeah.
Good. So, good evening, ladies and gentlemen. My name is Sergei Pankratov. I'm a third-year student of Moscow State University, physics faculty, semiconductors and cryo-electronics department. And I'll present MOF analysis methods to you. So here is the structure of my talk. Firstly, I'll define what MOF means. Secondly, we will consider the properties of these structures. Afterwards, we will talk briefly about the possible applications. Finally, I'll represent basic MOF analysis methods. And in the end, I'll make a conclusion. Dear colleagues, now I'm ready to start my report. So let's give the definition at first. MOFs are composite materials consist of organic and inorganic parts. The organic component contains large part of functional organic molecules, ligands, while the inorganic one is made of metal atoms. In fact, these structures have been familiar to chemists in the middle of the 18th century. They have learned how to explore, produce, and customize their properties very well. The plenty of metal centers and ligands combinations provides a high structural reliability. By now, more than 20,000 metal-organic frameworks are studied. The following thing to discuss is the characteristics of these structures. The most salient MOF properties are big unit surface area, high porosity, and as a consequence, low density. Also, MOFs offer high absorption capacity and selectivity for certain chemicals and compounds. Physical properties of MOFs can be customized with appropriate constituent choice and the ability to be modified by external factors. The most promising feature of MOF is self-assembly that can simplify the complex and hardly reproducible process of a nanostructure fabrication. So MOFs have many possible applications. For instance, metal organic frameworks can be used as hydrogen storage medium. Safe and inexpensive hydrogen storage is one of the main technological problems of hydrogen energetics and transport, and MOFs can provide an appropriate solution. These structures can serve as catalysts for chemical reactions in gas selective filter membranes. The idea of their use as active nano-electronic components seems to be the most challenging one. This tendency can lead to the emergence of qubits and neural networks of new generation, and I'm directly involved in their development. Unfortunately, metal organic frameworks can be seen in a scanning electron microscope, as in the pictures, because MOFs degrade under a beam of electrons. However, their structure and properties can be imaged with more exotic methods I'm about to present. The first technique I'll consider will be the Brauner-Emmett-Teller method, or shortly BET. It enables you to estimate the specific surface area and material porosity, the ratio of the overall surface of the materials to its volume or mass. And aim of BET is to obtain the absorption dependence on pressure at a constant temperature. Then we can estimate the biggest number of absorbed molecules using the BET formula. Here, big gamma is a number of adsorbed molecules. Big gamma m is their maximum number. P stands for pressure. PS stands for saturated pressure, and B is an absorption constant. Absorption coefficient. If the area of a single adsorbed molecule is known, it's possible to obtain the specific surface area. Physicists and chemists use powder X-ray diffraction to study the parameters of the crystalline structure. X-rays have high penetration capability and can go through atomic layers or reflect from a lattice site and interfere. From the interference maximum condition and basic geometry, we can get the Bragg's law, from which we are able to obtain the lattice parameter D that uniquely identifies a substance. The result of the PXOD procedure is a radiograph by the peaks of which the structure and composition of a substance are determined. MOF thermal sustainability is studied with the thermogravimetric analysis, TGA. The idea of the method is to observe the mass of the compound increase in temperature, and the faster the mass changes, the slower the further heating is. That provides a high precision degradation temperature determination. This method is often used in conjunction with a mass spectrometer that allows you to determine the chemical composition of vapors. The last tool we will consider will be mercury pyrometry method. In fact, it's necessary to apply excessive pressure to press a non-wetting liquid into a porous sample. This pressure is related to the pore size by the Washburn equation. Here it is, where R stands for the pore radius, gamma is mercury surface tension, theta the wetting contact angle, and P is the penetration pressure. This method refers to destructive analysis because the polymer structure deforms or collapses within colossal pressures. Thus, I've told you the basic approaches to the analysis of metal-organic frameworks, and now let's make a conclusion. In this work, I have told you what a MOF is. I have pointed out properties and possible applications of metal-organic frameworks, as well as the specifics of their research, and on the example of 4 investigation methods. Thank you for your attention. If there are any questions left, I'm ready to answer them.
Sergey, yes, I have one question. First, thank you for your presentation. It was quite clear for me, but I have one question. I made a note for me, not to forget this, and it is not quite clear what an adsorbate is and what an adsorbent is. Could you specify, please?
Yeah, sure. So the adsorption process creates a film of the adsorbate on the surface of the adsorbent. In other words, the adsorbate is the settling compound and the adsorbent is the hosting one. I hope I've answered your question.
Thank you. Now I understand. Thank you very much.
Another questions?
And I have another question. MOFs have probably some kind of pore inside distribution. How is it studied?
Yes, you're right. There is some kind of there is a pore size distribution. This distribution in MOFs and other porous materials is usually studied with BJH methods, and it represents some kind of a numerical model that complements the BET method I have mentioned above. And this method, this technique, requires disruption curve, so that's why I haven't mentioned it. But does that answer your question?
Thank you very much.
You're welcome.
Perfect. Thank you, Sergey, for your good presentation. So let us greet our next speaker. He is Alexey Moiseyevsky. Let us greet him. We don't hear you.
Probably that's better. Can you see me?
Yeah.
Okay.
We hear.
Can you see my screen?
Yeah.
Yes.
Oh, perfect. Why can't I? Oh, okay. I'm ready to start. Thank you. Good evening, ladies and gentlemen. My name is Alexei. I'm a PhD student of MSU Quantum Technology Center, and my subject is development of quantum computers, architecture, and software. Today, I want to present you a brief review for quantum supremacy question and modern state of quantum computing. Here are top references of my report. The main article is Information Scrambling in Computationally Complex Quantum Circuits, but it's so complex and difficult to understand that I decided to not go deep down into details and give you more interesting colorful pictures instead. So I got some other references to make my presentation a little bit easier. My report outline is following. Firstly, I want to tell you about what quantum supremacy is and actually what is this hype all about. Then we will consider several modern methods of quantum computing, quantum supremacy demonstration. And finally, I will tell you about the latest approaches in this field of study. So let's start from the beginning. In 1981, Richard Feynman said, the nature is not classical, and if you want to make simulation of nature, you'd better make it quantum. That's the moment where the story of quantum computing supremacy begins. For real, the idea of quantum supremacy is quite obvious. A quantum computer can perform natural laws natively when classical is limited by digital approach. But can quantum computer really do something that's in principle impossible for a classical one? And here we go to the definition. Quantum supremacy is a qualitative advantage of quantum computers over classical ones. To speak strictly in terms of computational hardness theory, we need to consider two fundamental classes. Look at this nice picture on the right corner of my slide. Here, BPP stands for set of problems that can be effectively solved with classical probabilistic Turing machine. And BQP, the green one, stands for the set of problems that can be effectively solved using quantum computer. So the question is BPP greater than BPP or not? And just look on this nice little equation on the left corner. Really cute, isn't it? The problem was pretty nice. The problem was that nice that from 1981 to 2019, nobody had even tried to give the final answer. But in October 2019, Google AI Quantum published a paper about quantum supremacy demonstration, and here we move to the next part of my report. Demonstration methods, random socket sampling, cross-entropy benchmarking, and lots of other beautiful terms. Let's consider random socket sampling firstly. Another nice picture for you here. Suppose we have a quantum register with some qubits in zero state. Let's apply some gates to it and let's shoot the gates randomly. The only thing we need to worry about is that after some time, all neighbor qubits will be binded and entangled by two qubit gates. Then let's measure our qubits in computational basis. In this way, we will obtain 0 or 1 from each qubit in our register, and whole register will be converted to a bit string. That's called random socket sampling. Of course, these bit strings will not be constant because quantum measurement is a probabilistic process. So, what do you think the bit strings probability will look like? Once again, we choose gates randomly, no other limitations. So you may think that distributions of the string probabilities will be uniform. That is completely right in case of classical algorithms, but it appears to be completely wrong in case of quantum computing. The distribution is exponential, and that's called Porter-Thomas distribution. And that's a strong signature of quantum chaos in our system. One day, guys from Google AI Quantum, led by John Martinez, found this phenomenon really interesting. And as you know, Google is a commercial company, so they found a way to get the profit from this. They developed a method to numerically estimate the power of any computer using random socket sampling. Firstly, we need to do the sampling using classical CPU, and where we will get the nice accuracy, but horrible time. And then we need to perform the same quantum circuit using quantum processing unit. After that, we will get the bit strings from both of our algorithms, and from the probability distribution of these bit strings, we will get the value called cross-entropy benchmarking fidelity, XIP fidelity, FXIP, as you can see. The point is that from XIP fidelity, we could be averaged over many random algorithms. So that's a value to estimate only the computer, not the particular algorithm. And finally, the experimental values of XIP fidelity will lead us to conclusion that quantum computer can, in several hours, do something that will get the classical computer for several thousand years. How do you take it? And right here, at the culmination of my speech, we'll move to the latest approaches in this field of study. The first one is that you can observe the real-time error propagation in qubit register. Here I prepared a small movie. The synthetic bit flip error appeared in the left corner of the qubit register, and qubits that were affected by error and were entangled gates with other affected qubits are marked with orange color. And the z-axis stands for the qubit projection difference between register with the error and the clear register. You can clearly see the kind of error wave front moving from left to right. Finally, it leads us to the beautiful phenomenon called quantum butterfly effect. It's really important to give nice names to the phenomena you discover, isn't it? By the way, there are two ways to describe information scrambling in quantum systems. Quantum entanglement in Schrödinger's approach, where operators are constant and the wave functions evolve, and the quantum scrambling in Heisenberg approach, where quantum states are constant and the quantum operators evolve. And it appeared to be much more convenient to describe quantum butterfly effect in terms of quantum scrambling. To do this correctly, we need to consider the ancillary qubit that will be entangled with one qubit from the register. And the source of error butterfly operator is located between two conjugated random quantum circuits. My presentation almost came to its logical end, has almost come to its logical end. Several final pictures left. Here you can see the error propagation again, but without any moves. On the top, the entangling gate is E-swap and E-swap square rooted on bottom. You can see how the influence of the error grows with time. And on this figure, Scholar shows the number of qubits affected by butterfly error. You can see that affected by butterfly operator, I'm sorry. You can see that as more far the butterfly operator is from the observed qubit, as longer it takes for correlations to drop down to zero. And on the right figure, you can see that where y-axis stands for renormalized so-called out of time order correlations. You can see that starting from some depth that is enough for error to propagate all over the register, all correlations rapidly drop to zero. That means that starting from this point, this whole state of register is completely chaotic, chaos everywhere. So that's all I wanted to tell you about. Thank you for attention. In case there are any comments or questions, you're welcome to ask and I'm ready to answer.
Yeah, Alexei, I have one question. Does the quantum supremacy demonstration via cross-entropy benchmarking give us the final answer about BPP and BQP classes relation?
Thank you. That's a really interesting question because there are great discussions about this point in the scientific community right now. Just 2 weeks ago, Chinese scientists presented an article where they perform the classical simulation of cross-entropy benchmarking via 16 graphics cards of NVIDIA Tesla type in 60 hours, if I'm right. No thousands of years, no even months, several thousands. is enough to complete cross-entropy benchmarking. It's still more than quantum computer will. This time is still a bit more than quantum computer that is required for quantum computer to solve cross-entropy benchmarking. But it is a great question. Do we understand the algorithms theory enough to do such conclusions, to make such conclusions? Because there are still no fundamental theoretical approaches to prove that BQP class is greater than BPP or not. So we can't say for real, is it or not? But if you want to take interest, to attract interest on markets, you need to understand that right now quantum computer can do more than classical.
And what is the main perspectives of quantum computers' practical use?
Yeah, thank you. The main ways of using quantum computers right now is the quantum chemistry. Quantum chemistry and some problems of logistics and fundamental optimizations, I should say. Even now, some commercial concerns like BMW, for example, are using quantum computers to optimize the delivery of different parts, to optimize their business, and they're taking real profit from it, probably. So right now, two fundamental ways are math optimization and quantum chemistry. But in future, probably when quantum computers will grow and become powerful enough, we will get to the point when quantum computers will become able to block classical cryptography.
Okay, thank you for your answer. It was pretty interesting.
Could I also ask a question? Can you predict when the quantum computers will be accessible for personal users?
Yeah, thank you. Another nice question. Right now, they are already accessible for personal use. You can visit sites of IBM Quantum, of Google AI Quantum Department, of Rigetti Computing, and probably in several months, quantum computing servers will be available on the site of even MSU Quantum Technology Center. Right now, we have a closed beta testing of our remote access to quantum computers. And when we will solve all problems with hardware, with information security, we will open it to whole web for personal use.
So we do have to bother it with it right now. Thank you.
Okay. Thank you.
If there is no any questions, so let us thank our guest. And our next speaker is Matveyeva Alexandra. Let us greet her.
Hello.
Hello.
Can you see my presentation?
Yeah.
Yes.
That's great. Good evening, ladies and gentlemen. My name is Matveyeva Alexandra. I am first year master student of physics faculty. I specialize in mathematics. Today, I am going to present you my personal research in mathematical biology. Its title is The Distribution of Beautiful Seashells by Depth. Here is the plan structure of my talk. Let's start with mentioning a few facts in introduction, move on to the main part. Furthermore, I will consider two examples. That will bring us to graph and its interpretation. Finally, I'll make a conclusion. Seashells have attracted people for centuries. Since ancient time, people have collected them use them as instruments and the basis of an art object. The complex geometry and the embodied harmony of color and form make them even more attractive. Seashells cause fascination and interest, but the most beautiful ones are quite difficult to get as they often lie very deeply. How many meters can you dive, my colleagues?
Maybe 3-4 meters, sorry.
Oh, that's great.
Or 2 meters.
Oh, it's nice. You can see beautiful fish in water. Shells are hard body coverings of some animals such as snails, bivalves, or barnacles. To protect their soft, vulnerable body, mollusks secrete a substance consisting mainly of calcium carbonate, which hardens into material similar in density to marble. There are 5 main classes of mollusks: bivalves, gastropods, shellfish, shovelnose, and cephalopods. Representatives of each of them have their own type of shells. Many seashells, especially bivalves, can be easily thrown on the shore. That's why it is easy to get them, and probably everyone has some of them at home. Does anyone have such seashells at home?
Of course.
Yes, of course.
Yeah, nice. But big and beautiful shells almost never lie on the shore. Diving away from the shore, one can find amazing shells. I think that there is a Gaussian distribution of beautiful shells by depth. This model is valid from 0 to 200 meters. That is all the depth to which sunlight reaches. I'll use Seashells, a brief identifier by Victor Yershoff and Yuri Kantor. I'm going to count the number of beautiful species at each depth. Let's take the minimum depth at which a shell can be found. It is necessary to introduce a criteria for the attractiveness of shell. I'll consider beautiful shells which have interesting color or pattern, or admirable geometry. Examples. The limpet. The limpet has no beautiful geometry. It has no beautiful pattern. It is small and gray. It is easy to find it on the seashore. There is no necessary to go into the water. It often grows on the bottoms of ships. And personally, I don't like it very much. How do you think? Is the shell beautiful?
No, I think.
Okay, thank you for your opinion. Let us consider the crest of Venus. Its shape is adorable. Its color has a bone-like hue, and there is a swollen pattern on the shell. This shell will impress any collector, but unfortunately, it is not easy to get it. This shell lies at a depth of 20 meters or more. This shell is beautiful, isn't it?
Yes.
Yes, of course.
Basing on the book, let's build a distribution diagram. The abscissa axis shows the depth in meters. The ordinate axis shows the number of beautiful species which live at the given depth. You can see from the graph that the most beautiful shells can be found at a depth of 20 to 30 meters. Sunlight penetrates this area well. There is always enough food on the depth, and the water isn't very cold. The deeper it is, the less light reaches the living organisms. But why then are there not so many beautiful shells near the shore? Most likely to avoid attracting the attention of those who can easily pull it out and eat it. To conclude this work, I will sum up what has been said. We looked at the main types of shells, introduced a criteria, studied beautiful photos, and built a graph and interpreted it. We arrived at the conclusion that to get the most beautiful shells, we must be able to dive deep. To do this, we can use Aqualung. Seashells are beautiful creations of the seas and oceans. Thank you for your attention. If you have any questions, feel free to ask me.
Okay, Alexandra, thank you for your interesting report. I have one question. In which ocean does the Venus crest inhabit?
Oh, this beautiful shell is native to Indo-Pacific waters.
Okay, interesting. Thank you.
Thank you for your question.
And I have a question. So do you have any metrics as a mathematician to investigate whether the shell is beautiful or not? Or you have some ideas, so you do it biased or?
Oh, this metric is very simple. If a shell has beautiful pattern or admirable geometry, I'll think that this shell is beautiful.
I got it, thank you.
Thank you, Alexandra, for your good presentation. So the next topic is dedicated to my personal research. So I'm going to share with you my own presentation. Give me some seconds. Okay, I'm ready. Can you see my screen?
Yeah.
Yeah.
Perfect. So my work is called An Overview of Neutral Atom Traps and Fabrication of Atom Triads in an Optical Dipole Trap. So, good evening, ladies and gentlemen. My name is Shampletov Nikita. I am a third-year undergraduate student of the Faculty of Physics, and my specialization is atomic optics. Today, I'm going to make an overview of atom traps and describe a process of atomic triad fabrication. Here is the structure of my talk. Firstly, I will start with introduction. Secondly, I'll pass over to traps overview. Furthermore, we will discuss optical tweezers a little more detailed. Then I'll describe triad fabrication process. And finally, I will make a conclusion. Let's start with introduction. Why do we want to trap the triad in a little optical trap? The size is typical about 1 micrometer. So there are many scientific and practical interests. From the viewpoint of science, such experiments give us valuable data about the evolution of three-body systems. On the other hand, understanding of such atomic processes will allow us to load traps more efficiently and thus make some improvements in quantum computations with cold atoms. The next place in our atomic journey is an overview of the methods of neutral atoms trapping. There are some types of traps: radiation pressure traps, magnetic traps, and optical traps, or optical tweezers. The main principle of radiation pressure traps is the law of conservation of momentum. When an atom consumes a photon, it receives its momentum, and so atom changes its velocity. In particular, an atom may be slowed down. Then, magnetic traps utilize the Zeeman effect, shifting energy levels under the presence of magnetic field, in particular in the presence of electromagnetic light, in the presence of light. And finally, optical dipole traps or tweezers. They are based on the so-called AC Stark effect or Otler-Towns effect. This effect is the energy levels shifting due to the presence of alternate electromagnetic field, in particular under the presence of light that I have mentioned before. Now, When we have finished our short review of the main types of traps, we can think about what types is the best. The answer is simple. There is no the best one, because each type has its own benefits and weak points. Let's list main characteristics of the traps. Radiation pressure traps. Its typical depth is about a few Kelvin. It allows to capture and accumulate atoms from thermal gas. And trapped atoms can be cooled down to a few tens of microkelvins. This restriction is caused by high light-induced excitations. Then, magnetic traps. Its typical depth is about 100 millikelvin. These traps are excellent tools for Bose-Einstein condensation, and it has a noticeable restriction. Trapping mechanism relies on inner atomic structure, so we can't conduct experiments with changing of that structure. And finally, optical tweezers. Its typical depth is less than 1 millikelvin. It has low light-induced excitations, and under appropriate conditions, the trapping mechanism is independent of inner structure. The fabrication method I wanted to describe utilizes optical dipole traps, so let's pass over to them. Optical tweezers. Main effect of optical dipole traps is the AC Stark effect. Under the presence of light, electromagnetic wave, energy levels are shifting. The value of shifting is given by formula, this big one formula, where gamma is damping rate, omega is the light frequency, omega 0 is the resonant frequency, I is the light intensity. And usually in practice, the light frequency and the resonant frequency are close to each other. It means that the second term in the equation is negligible compared to the first one. So the formula simplifies to that formula, the short one, where delta denotes omega minus omega 0 and called detuning. We may note that the potential described by the formula above can be positive or negative depending on the sign of detuning. When the light frequency is lower than the resonant one, that is red detuning, the potential is attractive. And when it's higher, that is blue detuning, the potential is repelling. At that moment, we are ready to discuss the method of triad fabrication that I have announced at the beginning. The process starts by isolating 3 atoms in 3 optical tweezers, shown in the picture here. A lens focuses 3 steerable lasers beams to a spot size of 1.1 micrometer to form the tweezers. Using an acousto-optic modulator, the 2 outermost tweezers are steered closer to the central one until they all merge. The duration of this manipulation is about 40 milliseconds, and the final spacing in the merged state between the centers of the 3 steerable beams is 0.85 micrometers. After ramping up the 2 outermost tweezers adiabatically in 30 milliseconds, the single tweezer beam holding 3 atoms ramps adiabatically from 5 milliwatts to 170 milliwatts. That process looks pretty simple, but there is a hidden problem: loss processes. So the rate of these processes depends on experimental conditions. There, I want to show you some experimental data that allows us to control the losses. Wait time, this axis and this axis. Wait time is the time from the merging moment to the moment of the trapped moment of the trapped atoms population detection. The figure presents example plots of the population dynamics in a tweezer with a beam power of 170 milliwatts. When the probability of observing 3 atoms, red diamonds, decays, the probability for observing 1 atom, yellow stars, or 0, blue squares, atoms grows. The probability for observing 2 atoms remains effectively 0 for all times, showing that single atom loss is negligible in the experiment. That's enough for an overview. For those who are really interested in, I'll show a list of literature I've used in the end. And now, dear friends, I'm ready to make a conclusion. Today, I've told you about main types of neutral atom traps, namely radiation pressure traps, magnetic traps, and of course, optical dipole traps or tweezers. Also, I've described the method of fabrication atom triads and present some data representing the rate of loss processes. And I believe I was able to show you the beauty of atomic optics in a short way. So, my presentation has come to its logical end. Thank you for your attention. In case there are any questions, I'm ready to answer them and hear literature.
I have a question. What is typical power of lasers used in such kind of experiments?
So the typical power is about some hundreds of milliwatts. You can see some lasers with power about 1 watt, but that is really powerful laser, and probably that is argon laser. So the typical energy, the typical power is 100 milliwatts.
Thank you.
So, if there is no questions anymore, we will continue. And the next speaker is Елизавета Murga. Let us greet her.
Thank you very much. Can you see my presentation?
Yes.
Okay, let's start. Good evening, ladies and gentlemen. My name is Murga Elizaveta, and I'm a third-year undergraduate student of Moscow State University Physics Department. I specialize in biophysics. At our last scientific conference, I presented to you my research in the field of neurodegenerative diseases, which was also related to the concept of the chirality of biomolecules. This time, chirality also wouldn't avoid us. Today, I would like to share the research of my colleagues, Ekaterina Semyonova and Ekaterina Malishka, with you. It's about chirality of medicine drugs. Today, we will talk about why is the chirality of biomolecules important, what are enantiomers and how do they differ, why do you need to know where is the medicine rotates, where is the right better than left and in contrast, and to sum up. Dear colleagues, let's start, shall we? Okay. First, you need to understand what biomolecules are. Biomolecules are organic substances that are synthesized by living organisms. The composition of biomolecules includes proteins, polysaccharides, nucleic acids, as well as smaller components of metabolism. We are made up entirely of biomolecules. From their assembly and interaction, the living becomes alive. This is where the chirality of these biomolecules come into the play. Chirality is the incompatibility of an object with its mirror image by any combination of rotations and movements in three-dimensional space. A classic example is our hands. Look at them. No matter how we twist them, you can turn them exactly the same way. So it is with biomolecules too. Chirality is a characteristic defined as a so-called isomeres and divides biomolecules into the right D or R isomeres and left L or C isomeres. In living organisms, one type of the types of chiral molecules is often represented. For example, the amino acids in our body are left and sugars are right. And the interaction between the molecules also has a certain pattern or chirality. Moreover, with the complication of the structure of the biomolecule, there is a tendency to change the sign of chirality to the opposite. So the protein is folded, what you can see on the right part of screen. It moves from the left chain of amino acids to the right helix and then to the left tertiary structure. At the same time, the macromolecules of the same level of complexity tend to interact in the space of the same type of chiral symmetries. And multi-level ones interact in pairs of different types of chirality sign. This also applies to intramolecular interactions. Therefore, the chirality of molecules is so important for any living organisms. Now we need to find out what are enantiomers and how do they differ. The concept of chirality is a characteristic of any incompatibility of an object with its mirror image, whether it's molecule or you and me. In chemistry, for chiral chemical compounds, there is a concept of stereoisomers. By definition, stereoisomers are chemical compounds that have the same structure but differ in a spatial arrangement of atoms. There are different types of isomers, but we will be interested in enantiomers. Enantiomers is a pair of stereoisomers that are mirror images of each other that are not aligned in space. Since an object can have only one mirror image, enantiomers exist in pairs. Enantiometric molecules have the property of chirality, which is not surprising. That is, they don't match in space with the mirror image. Enantiomers can have the same physical and chemical properties, but differ in the optical activity, characterized by the direction in which they rotate plane polarized light. You can ask me, why do you need to know where the medicine rotates? Now, after getting familiar with the basic concepts, let's move on how chiral enantiomers and drugs are related and why is this so important. However, enantiomers, including medicine drugs, can interact with chiral molecules of living organisms in completely different chemical and biological ways. When creating drugs, it's extremely important to take into account the specificity of the interaction of enantiomers with asymmetric compounds of our bodies. Since that, it may turn out that only one form of the drug has a positive effect. At the same time, the other can cause serious side effects by being toxic. Look at your screens now. Do you know who is it?
Yeah,
Somebody?
that is Nick Vujicic.
Yeah, that's right. It's Nick Vujicic, an Australian motivator, philanthropist, and writer, born without all four limbs. No hands, no legs. Scary. This disease is called phocomelia and is a consequence of the incorrect chirality of the medicine drug that pregnant woman took as sedative. This medicine is called thalidomide. If you have heard about the thalidomide scandal, you know that in the period from 1956 to 1962, in a number of countries around the world, according to various estimates, amazing about 10,000 children were born with bodies deformations and limbs on limbs and organs. And the reason for everything was that the left isomer of thalidomide interferes with embryonic development and causes disorders of the structure of organs and limbs. Now you should know where is the right better than left, and in contrast. Chiral drugs can be divided into 3 groups based on the chirality of the bioactive enantiomer. With a bioactive left S enantiomer, with a bioactive right enantiomer, and with 2 bioactive enantiomers. In the case when both enantiomers are active, the drug is created from the mixture in equal parts, obtaining the so-called racemate. I will give a couple of examples of modern chiral drugs. More of them you can see on diagram. Drugs with a bioactive left side as enantiomer are ethambutol, which is used in the treatment of tuberculosis, and penicillamine. The right bioactive drugs include the well-known thalidomide. It was his left S enantiomer that caused the consequence of scandal. And active in both sides are dextromethorphan and as a cough remedy and econazole. Let's sum up the results. More than half of the drugs developed in recent years consist of chiral molecules. Chiral drugs are used in the treatment of wide range of diseases, including cardiovascular and gastrointestinal diseases. Obtaining optically pure forms of drugs is complex and expensive task, but their use in many causes could reduce the dosage and the number of side effects of the drug. Unfortunately, the packaging doesn't indicate which drug you are taking, left or right, but pharmaceutical companies are increasingly paying attention to the fact of the chirality of biological molecules and their specific interactions. But I wish you would maintain your chirality without any medicine drugs. Thank you all for your attention. If you have any questions, I'm ready to answer them.
Wonderful.
Yes, good evening, everyone. My name is George, and I'm a student of Faculty of Fundamental Medicine. Elizaveta, can you explain to me how the left or right drugs interact in the chiral molecules in us? And why are their interactions so different?
Good evening, George. Thank you for your question. I will start with differences in the effect of drugs on the body. So far, the physical nature of the differences in therapeutic effects from left and right drugs is not fully researched. The researchers of our department believe that it's possible to understand the interaction of chiral drug and chiral molecules of our body through the hierarchy of biological molecules in the change of the sign of chirality. And speaking of interaction with our chiral molecules, the therapeutic activity of enantiomers, their pharmacological kinetics and dynamics are being intensively studied. In addition to the difference in metabolism and distribution in living organisms, there is also a process when one chiral enantiomer into our body turns into another, which makes it difficult to determine the therapeutic effect on the body of the desired isomer.
Nice, thank you.
Thank you, Lisa, for your splendid work. Our next speaker is Maxim Lenivkin. Let us greet him.
Okay. So I'm ready. Let's start. Okay. Well, good afternoon, ladies and gentlemen. My name is Maxim Lenivkin, and I am third year undergraduate student of physics faculty of MSU. I specialize in the physics of accelerators and the radiation medicine. I'm going to tell you about the radiation therapy. So, first of all, I explain you what radiation therapy is, then I'll tell you about the side effects of such therapy and the mechanism of its action. Furthermore, the external beam radiotherapy will be mentioned, and finally, I'll talk about brachytherapy and unsealed source radiotherapy. So, dear friends, let's start, shall we? Radiation therapy or radiotherapy is a therapy using radiation. Generally, it's used as part of cancer treatment. This technology is applied to control and kill malignant cells. Normally, the radiation is delivered by a linear accelerator. Before treatment, a CT scan is often performed to identify the tumor and surrounding normal structures. The patient receives small skin marks to guide the placement of treatment fields. Patient positioning is crucial. At this stage, the patient will have to be placed at an identical position during each treatment. Many patient positioning devices have been developed for this purpose, but we'll talk about them later. Unfortunately, radiation therapy has some significant drawbacks. In fact, all in all, it's unsafe, painless. Moreover, low-dose treatment usually causes minimal or no side effects. Also, short-term pain flare-up can be experienced in days days following the treatment. Nonetheless, higher doses can cause varying side effects. The nature, severity, and the longevity of side effects depends on the organs that receive the radiation, the treatment itself, and the patient. All in all, side effects can be pretty severe. For instance, possible late side effects include cardiovascular diseases, cognitive decline, and effects on reproduction. Speaking about the mechanism of its action, the radiation therapy works by damaging the DNA of cancerous cells. The DNA damage is either direct or indirect ionization of atoms which make up the DNA chain. Indirect ionization happens as a result of ionizing of water, forming free radicals which damage the DNA. Cells have mechanisms for repairing single-strand DNA damage and double-stranded DNA damage. However, double-stranded DNA damage is much more difficult to repair. And also it can lead to dramatic chromosomal abnormalities and genetic deletions. Targeting double-stranded breaks increase the probability that cells will undergo a cell death. Cancerous cells are generally less differentiated and reproduce more than most healthy cells. Also, they have diminished ability to repair sublethal damage. Single-strand DNA damage is then passed through cell division, causing them to die or reproduce more slowly. So that's how the cancer dies. The external beam radiotherapy is the most common form of radiotherapy. The patient lies on the couch, and the external source of ionizing radiation is pointed at a particular part of the body. The radiation is directed at the tumor from outside of the body. X-ray and electron beams are by far the most widely used sources of external beam radiotherapy. So, the external beam radiotherapy is pretty comfortable and it's commonly used well everywhere. A novel way of applying external beam radiotherapy is CyberKnife. It's actually a radiation therapy device. The system is used to deliver radiosurgery and for the treatment of malignant tumors and some other medical conditions. The device combines a compact linear accelerator mounted on a robotic manipulator, an integrated image guidance system. The image guidance systems acquire stereoscopic images during treatment, which tracks tumor motion and guides the robotic manipulator to precisely and accurately align the treatment beam to the moving tumor. In fact, it's actually a great solution to the problem of positioning the patient. Indeed, the device wonderfully manages to make the therapy as much comfortable as it's possible for the patient. Also, it contrasts with other less appealing but still probably more practical solutions which usually uses a special device to fix the head of the patient to keep it still. Well, on the other hand, there is a brachytherapy. In this therapy, the radiation source is inside the body. A sealed radiation source is placed inside the neck, inside or next to the area of the requiring treatment. Brachytherapy can be used alone or in combination with other therapies such as surgery, external beam radiotherapy, chemotherapy, and others. The brachytherapy uses radionuclide, which remains in the capsule or metal wire during treatment, and it needs to be physically placed near the treatment position. In contrast, in unsealed source radiotherapy, a therapeutic radioscope is injected into the body to chemically ionize to the it's injected to the body to chemically ionize to the tissue requiring destruction. It uses physical and chemical and biological properties of the radiopharmaceutical to target areas of body for radiation treatment. The released diagnostic modality for nuclear medicine employs the same principles, but still different. But it uses different types of or quantities of radiopharmaceuticals in order to image or analyze functional system within the patient. Well, in summary, I've told you about the radiotherapy. I've discussed its mechanism of action and the side effects of such therapy. Moreover, I've told you about the external beam radiotherapy, and in the end, brachytherapy and the sealed source radiotherapy were regarded. In conclusion, I'd like to emphasize that the radiation therapy is an incredibly important way of treating cancer. It's a marvelous technology which is used to save a great number of people's lives. Nonetheless, as I've demonstrated, it does have several pros and cons. Thank you for your attention. If there are any questions, I'm ready to answer them.
Yeah, thank you very much for your presentation. And I've got a question. And you've talked about some systems, and you said that you should the position is very important of the patient for the such systems. And why is it such important?
The answer is pretty obvious. We need for our radiotherapy to be effective at the same place all the time. You know that the radiotherapy doesn't only destroy cancerous cells, it also destroys the organs near the place where the treatment is taken. And so if we cannot assure that we always put our radiation at the same place, our treatment will be pointless. We'll just damage the organism and we won't kill the cancerous cells. Well, okay. That's actually the reason.
Yeah, thank you.
So
thank you, Maxim, for your good presentation. And the next speaker is Daria Kuznetsova. Let us greet her.
Okay, 1 second. Friends, is the presentation visible?
Yes.
Yes, it is.
Okay. Good evening, ladies and gentlemen. My name is Daria Kuznetsova. I'm a first-year master student of Moscow State University, Physics Department. I specialize in physical math. Today, I'm going to consider the problem of big data. Here is the structure of my talk. Firstly, I will tell what big data is. Then I will speak about the methods used to analyze big data and their applications in solving physical problems. Finally, I will sum up all that I will say. Dear friends, let's start. To begin with, big data is a term that describes large volumes of high velocity, complex and variable data that require advanced techniques and technologies to enable the capture, storage, distribution, management, and analysis of the information. Big data is often described with 3 V's. Volume refers to the magnitude of data. Big data sizes are reported in multiple terabytes and petabytes. What may be deemed big data today may not meet threshold in the future because storage capacities will increase, allowing even bigger data sets to be captured. Rarity refers to the structural heterogeneity in a data set. Technological advances allow firms to use various types of structured, semi-structured, and unstructured data. Structured data constitutes only 5% of all existing data. Text, images, audio, and video are examples of unstructured data, which sometimes lack the structural organization required by machines for analysis. Velocity refers to the rate at which data is generated and the speed at which it should be analyzed and acted upon. How can we analyze big data? The first method is association rule learning. It is a method for discovering interesting correlations between variables in a large databases. It was first used by major supermarket chains to discover interesting correlations between products using data from supermarket point of sale system. The second method is genetic algorithms. They are inspired by the way evolution works, that is, through mechanisms such as inheritance, mutation, and natural selections. These mechanisms are used to evolve useful solutions to problems that require optimization. The third method is machine learning. It includes software that can learn from data. It gives computers the ability to learn without being explicitly programmed and is focused on making predictions based on known properties learned from sets of training data. Let's change the subject and consider big data applications in computational physics. First of all, within this area, data sets are almost always accurate. It is created with the sole purpose of being studied. Using such data sets allows computer models to achieve a much higher degree of accuracy than conventional computer simulations. Big data analytics with computational physics are quite cheap compared to real-world simulations. Even predictions can be made using much larger data sets. The most evident, for example, in the field of climatology. Let us over to an example of the use of big data in the field of soft body physics. A team of computer science researchers at Brown University used computer simulations of soft body physics and predictive analytics and to determine the behavior of wide range joints in the human body. The team was able to achieve only 74% accuracy. By combining predictive analytics and big data, the team could achieve a much higher degree of accuracy. The ability to maintain accuracy online is a very important goal in making simulation more relevant to real world. Since soft-body modeling is significantly less complex than galaxy models, it is highly likely that machine learning combining with big data can be used to reduce the computational time of complex soft-body simulations. Dear colleagues, today I have enlarged your knowledge in the sphere of big data. Now I'm ready to make a conclusion. To conclude, I would like to say following. Firstly, big data describes large volumes of unstructured data that need to be investigated. Secondly, popular methods to analyze big data are association rule learning, genetic algorithms, and machine learning. And last but not least, big data can be applied to various fields of physics. Thank you for your attention. In case there are any questions, I'm ready to answer them.
Daria, I have one question. What an interesting example of the use of big data technology do you know?
Thank you for your question, Alexandra. A good example of the use of big data technologies, in my opinion, is the COVID incidence model for Russia. Such model was built by Sber. I've been following the forecasts about 6 months on the site, and they are quite accurate. Following this model, Sber makes decisions about the format of employees' work during the pandemic. That is, it decides to work remotely or not. Thus, big data technologies can be useful in all areas. If interesting, site address is sberrindex.ru. That's all.
Oh, thank you. That's great.
Thank you, Daria, for your good presentation. So our next speaker is Anna Deputatova. Let us greet her.
Hello, everyone. Can you see the screen?
Yes, we can see it.
Yes.
Okay. So good evening, ladies and gentlemen. Again, my name is Deputatova Anna, and I'm a third year undergraduate student of Moscow State University Physics Department. I specialize in biophysics. Today, I'm going to present you a presentation about an extremely interesting observation. So here is the structure of my talk and the plan. First of all, I'm going to start with the introduction. Then I'm going to move to the main part, which consists of three basic parts. The first one is about platelet hemostasis, the second one is about thrombodynamics, and the last one is about my personal experiments. Finally, I'm going to end up with conclusions. So let me start. First of all, I'm going to start with introduction. Cancer cells pose the main threat to the normal functioning of the body due to their ability to divide uncontrollably. However, there is another danger, the presence on such cells of a tissue factor, the main activator of the plasma link of blood coagulation. Tumor cells, which carry tissue factor on the membrane and are able to circulate in the bloodstream, cause the formation of aggregates from platelets and cancer cells, which can lead to thrombosis and vascular blockages, for example. However, until now, no method has been created in which the theory of the growth of a fibrin clot directly from tumor cells would be confirmed. The most common reason is an uncontrollable thrombus growing that leads to the blockage of the vessel. It's a noticeably huge problem in the modern world and in the modern medicine. Moreover, without deep understanding of the growth of a fibrin clot directly from tumor cells, there is no exact method in the modern medicine to solve the problem. Well, let us move further and discuss a little more about platelet hemostasis. Blood clotting is a really complex process of cascade of enzymatic reactions. They are divided into three basic phases: initiation, spreading, and stopping of the coagulation process. Coagulation is activated by tissue factor, and the process of propagation deep into the vessel is regulated by reactions that form positive and negative feedbacks. The coagulation activator, a protein of cell membranes tissue factor, is localized in the damaged area and also locally forms a complex with factor 7A. Further thanks to the work of positive and negative also feedbacks and diffusion of active factors, the coagulation process spreads from the site of injury into the depth of the vessel without contact with the activator. That's how it works in normal processes. Well, to understand more about my personal work, we need to move further and let us look at this slide and discuss more carefully about platelet hemostasis. Well, thrombin is obtained from prothrombin in a similar process involving factor 10A. As it can be seen from the diagram, the chain continues higher. Factor 10 is activated by factor 9. Factor 9 is activated by factor 11. The system of enzymes activating each other, in fact, is called a cascade. The main entrance in the coagulation cascade is in the middle, just at the level of factor 10. This system of reactions is responsible for triggering the coagulation system, and the system is called the external coagulation pathway or tissue factor pathway. The main components of this pathway are two proteins, factor 7a and tissue factor. It was proved earlier that there is tissue factor on cancer cells, but no one before my scientific group has shown the exact growth of a fibrin clot directly from tumor cells. To show it, there was used a special method and special equipment which named thromboddynamics. Okay, now let me tell you more about this method which named thromboddynamics. Well, the thermodynamics method is based on direct observation of the growth of a fibrin clot in blood plasma after placing there a special insert activator in a measuring container with plasma. In our personal experiments, instead of placing there a special activator, we were placing there cancer cells which were attached to the glass with a special procedure which name is salinization, and also we used special antibodies. Well, observations were carried out by a special optical method, and it was something new in this field of study. Well, let us talk a little more about my personal experiments. Here on this slide, you can see on the left side, my personal experiments, how the fibrin clot is growing deep into the plasma. And on the right side, I showed you a special equipment which was needed for these experiments. So the computer and the thromboddynamics equipment. Let us now move further and discuss more about my personal experiments. Well, in my part of work, I was calculating the speed of clot growth in thermodynamics experiments to prove that the tissue factor is the main activator of thromb growth in plasma hemostasis. Here on your screens, you can see the dependence of clot growth from time. Also, we calculated other physical parameters such as area of a clot, density. In future, these results, I hope that they will probably help to understand more about the interaction between cancer cells and blood components. Also, there will be discussion about metastasis processes, and also we hope that this research will be carried out with a special blood components of real patients. Now I'd like to make some conclusions. Here on your screens, you can see also oncocells on the left side and on the right side as well. The plasma hemostasis system has a complex structure, but when it comes to the cancer cells inside the body, the processes are getting only more harder and complicated. There is still no certain answer about the mechanisms of interaction between blood components and cancer cells. Also, no one knows about the processes of metastasis, which are really common inside the body of real patients. In case of this research, such drugs will not treat the cancer, but they will prevent from such consequences as thromb growth and probably prevent people from suffering. Thank you for your attention, and in case you have any questions, I will try to answer them.
Hello, good evening. My name is Lena Konova, and I have a question. Have you also made other types of experiments to observe the interaction between thrombocytes and oncocells?
Well, of course, there is a huge number of such experiments. For example, I personally tried to make an electron microscopy, cytometry, and also there was an aggregation of platelets in the aggregation of platelets with oncocells. So as far as I remember, that's all, but probably we will try to make some more experiments in this topic.
Thank you, it's very interesting.
Thank you.
Let us thank Anna for her great work. So the next speaker is Konova Yelena. Let us greet her.
Can you see my presentation?
Yes.
Thank you. Good evening, ladies and gentlemen. My name is Elena Konnova, and I'm a first-year master student of acoustic department. I specialize in medical ultrasound, and my purpose is to tell you about the technical direction of ultrasound application. My topic is called the use of graphic accelerators in modeling ultrasound beams based on the Westervelt equation. This slide shows the outline of my report. Firstly, I would like to tell you about HIFU technology. Then I will present the theoretical model. Following that, we are going to consider implementation of calculations on the CPU and GPU and results. At last, we will make a conclusion. Dear colleagues, let me start and tell you about HIFU. Nonlinear radiation modes are increasingly used in medicine, for example, to implement diagnostics and methods of non-invasive surgery using HIFU it's necessary. In this regard, there are tasks such as the design of the transducers and the calibration field of transducers. There is need for multiple and multiparametric modeling of nonlinear ultrasonic beams. The Westervelt equation is often used to model nonlinear HIFU fields. However, simulations of three-dimensional beams take run times up to several days, even using high-performance service with multi-core CPUs, which makes rapid treatment planning unavailable. As you can guess, this is very long time, and we are talking about treating people, that is, we need it faster. This problem can be mitigated by using graphics processors, GPUs. In this project, an algorithm to solve the Westervelt equation on a GPU was developed in order to achieve significant acceleration over a CPU version. The next topic to discuss is theoretical model. The Westervelt equation includes three effects: diffraction, nonlinearity, and absorption. Calculations are performed using the coordinate along the z-axis of the beam. It's considered that a monochromatic wave is emitted, which is enriched with harmonics due to nonlinear effects while its propagation. At each step in Z, the sample pressure field is represented in the computer memory as a three-dimensional matrix that contains a set of amplitudes of 2 and max harmonics of the wave spectrum at each point in the XY plane. As you can see, the equation is complex, and there is a lot of data, and it needs to be solved. It's interesting that the Westervelt equation is solved by splitting by physical factors at each step of the algorithm along the z-coordinate. After decomposing the solution into finite Fourier series, a system of related equations is obtained for the complex amplitude of each of the harmonics as a function of coordinates. This definitely makes life easier. At each step of the algorithm along the z-axis, the half-step diffraction effect is first calculated using the angular spectrum method. For a two-dimensional spatial distribution of the complex amplitudes of each harmonic using the fast Fourier transform, we obtain a set of complex amplitudes of plane waves propagating at different angles to the z-axis. Plane waves propagate for the next half step along the z-axis by multiplying by a propagator. Then special distribution of harmonic amplitudes are collected using the inverse f of t. In the second step, the absorption is also calculated by half a step. After that, the calculation of nonlinearity for the full step along the z-axis is implemented. To do this, we solve a system of first-order ordinary related differential equations for harmonic amplitudes. The approximate solution of the system is constructed by the fourth-order Runge-Kutta method. After that, the absorption and diffraction operators are calculated again by half a step along the z-axis. Calculations of all operators are repeated in cyclic until the required interval is spaced along the z-axis. This calculation scheme allows for second-order accuracy in the z-coordinate. Let's talk a little about the processes themselves. In this paper, three algorithms were implemented in the C++ programming language: single-threaded for the CPU, multi-threaded for the CPU using OpenMP technology 4 and 8 threads, and an algorithm for the GPU using NVIDIA CUDA technology. GPUs have thousands of small cores that can perform various simple calculations in parallel. Central processors have several powerful cores that can perform several time-consuming tasks simultaneously. Do you agree that using the GPU is better for our task?
Oh yeah, I agree
Of
with
course.
Yes, absolutely right. We will check it soon. The FFTW and CUFFT libraries for CPU and GPU respectively were used for Fourier transforms. Now let's pay attention to the results. An example of modeling the field of a single focus transducer of 1 MHz frequency is presented. The amplitude distributions for the first 3 harmonics obtained at 8 CPU threads or at GPU are shown in figure 1 in Excel and focal planes of the transducer, demonstrating the correct implementation of the algorithms. The computational speed of the CPU increased proportionally to an increase in the number of threads, but the rate of computing on GPU was much higher. The acceleration of calculations for 10 harmonics with GPUs compared to CPU was 80 times for 1 thread of CPU, 20 times for 4 threads, and 8 times for 8 threads. When more harmonics were included in simulations, the acceleration increased proportionally to the number of harmonics. This is, we managed to significantly up the calculations. Dear colleagues, let's recall the main points of the report and consider the conclusions. In this report, we talked about the use of the HIFU technology, considered a theoretical model based on the Westervelt equation, which is used to describe sound beams, and compared the implementation of algorithms on the central and graphics processors. Let's sum up the results. The numerical simulations of nonlinear fields of a focused ultrasound beam for 10 harmonics are accelerated when using a GPU versus CPU. 80 times for 1 thread of CPU, 20 times for 4 threads of CPU, and 10 times for 8 threads of CPU. Acceleration increases in proportion to the number of harmonics. Thank you for the time. In case there are any questions, I'm ready to answer them.
Good evening, Helena. And I have one question for you. It's so big. Okay, why do you use the Westervelt equation to describe ultrasonic beams? Maybe there are other models to describe.
Thank you for the question. Yes, we can say about 2 more models. Since the source can be considered a point at the wave propagation scales, and the wave itself can be considered spherical, the Burgers equation can be used to describe its propagation. And to account for more physical phenomena such as nonlinearity and diffraction, the Khokhlov-Zabolotskaya-Kuznetsov equation is often used. However, the Westervelt equation allows for greater accuracy in the wider angle region of the beam. So, Westervelt equation is better.
Okay, understand. Thank you.
Thank you.
Thank you, Yelena, for your captivating presentation. So the next speaker is Daria Chupova. Let us greet her.
Do you see my presentation?
Yes.
Okay. So let's start. Good evening, ladies and gentlemen. My name is Daria Chupova, and I'm a first-year master student of acoustics department, as Elena, and I specialize in medical ultrasound. And today I'll present my work on aberration correction for the transcal focusing of high-intensity ultrasound at various depths in the brain. And here's the structure of my talk. And firstly, I'll talk about existing arrays for HIFU neurosurgery and current difficulties in this area. Secondly, I'll consider possible solutions for this problem and aim of my study. Thirdly, I'll discuss numerical methods which were used in my work. Then I'll present the results. And at last, I'll make a conclusion which demonstrates the main results of my work and future perspectives. So, dear colleagues, let's start talking about existing arrays for HIFU brain ablation and current difficulties of this area. So hemispherical multi-element phased arrays have been successfully used for thermal lesioning in deep brain structures. However, despite undoubted advantages of these transducers, there are several limitations in their surgical application. For example, hemispherical array geometry restricts its displacement, and thus the treatment envelope of such systems is limited to the central part of the head. So an important advancement of HIFU neurosurgery would be to enlarge the existing spatial region in brain accessible for the treatment. And that will bring us to the next point, which is about possible solutions of the problem. And recently in our laboratory, new design of multi-element phased arrays had been proposed. And these arrays have a compact shape of a spherical segment and random fully populated pattern of its elements. And it has been shown in our previous studies that they can provide pressure levels and degree of non-linear distortion required for mechanical destruction of the tissue in the focus and using buoyant hastotrypsin methods. Also, the array geometry allows for moving the transducer relative to the patient's head and thus potentially to enlarge the treatment region. And so the aim of my work was to demonstrate theoretically the possibility of such arrays for tight transskull focusing at different depths in the brain with aberration correction. So now let's talk about numerical methods which were used in the work. And for field calculation and aberration correction algorithms, a combination of two different approaches was used. An acoustic model of the head was reconstructed using segmentation of an MRI scan. And for field calculation, the Rayleigh integral was used for propagating in water outside the head to the plane boundary near it. And then pseudo-spectral time domain simulation based on the Kelvin-Voigt rheological model was utilized for propagation through the skin, skull, and brain to the focus. And aberration correction was based on phase conjugation methods, and first a spherically divergent wave propagating from the focal point to the boundary outside the head was simulated using K-wave. And then the Rayleigh integral was used to define phase delays at the geometrical centers of each element. And calculations were conducted for 5 different depths in the brain. And from the center of the head, which is pointed red on the left picture, the transducer was mechanically moved along its axis down for 1 centimeter and up for 1, 2, and 3 centimeters. And now let's move on to the next slide, which gives us information on the results of this work. And first, a simulation with aberration correction was performed at 5 focal depth for 256 elements array, and it showed that tight focusing was provided at 25 to 65 millimeter from the inner skull surface. And for shallow focusing, the intensity at the focus decreased for 18% compared to the head center. And then to improve the aberration correction, the number of elements was increased to 512 and 1024. And simulation for arrays with different number of elements showed that all arrays provided the same focal spot size as in water. And furthermore, intensity at the focus increased by 20% for the 512 element array compared to the 256 one. And for 1024 element array, intensity at the focus increased in additional 13%. So Dear colleagues, now I'd like to sum up the main points of my talk. Today, firstly, I've talked a bit about arrays for hyphenary surgery and difficulties existing in this area. Secondly, I move on to the possible solutions and the aim of my work. Then I discussed methods that were used in the work. After that, I presented the results. So to conclude, I'd like to say that this study demonstrates that the proposed new type of arrays can provide tight focusing through an intact skull, at least over a 40 millimeter range in brain, of depths in brain. And also all the arrays provide the same focal size after aberration correction. And 512 element pattern seems sufficient for tight and effective focusing. Also, for future work, it is planned to evaluate electronic steering capabilities of such arrays with aberration correction, consider internal skull and brain structure, and compare aberration correction algorithm with geometric approach. Thank you for your attention, and if there are any questions, I'm ready to answer them.
Thank you.
Well, Daria, I wonder, what diseases can be treated with HIFU?
Oh, thank you for a question. Yeah, that's a really good question. And as we can see here, we can ablate only central part of the head and its thalamus region. And we can treat, if these surgeries are approved, already approved, we can treat essential tremor and tremor which is caused by Parkinson's disease. And also under clinical investigations, there are depression and OCD, which is obsessive compulsive disorder. And also it is used to treat neuropathic pain. And if we use lower frequencies for not to damage tissue, but to for neuromodulation, we can treat epilepsy. And it is under investigation now.
Well, and are there any limiting factors for HIFU?
Yeah, of course, there are lots of limitations. And well, the main limitation, if we want to have a thermal effect at the focus, is temperature of the skull, because if we overheat the skull of our patient, the patient could die, which is undesirable result of our surgery, of course. And if we use boiling histotripsy method, which is for our new arrays, the limitation factor is a pressure level near the skull because it can cause cavitation, which can damage the skull and also which is dangerous for our patient.
Okay, thank you for your answer.
Okay, for questions.
Okay, let us thank Daria for her work. And eventually, our conference has come to its logical end. I do hope that you have enjoyed the time alongside with getting new knowledge. And now, I'd like to give the floor to the lecturer of the Mathematics Department, Andrei Andreevich Petokhov. Let us greet him.
Good evening. So I would like to make, I think, a short conclusion to this conference. So first of all, I would like to thank all the speakers. And today I have listened to 15 wonderful talks devoted to various fields of physics, and I have learned a lot of new things, I think. So I would like to wish all of you good results, some inspiration, I think, in your future research work. And of course, I would like to thank Amalia Deslavna for organizing this conference and for inviting me. Well, I remember more than 10 years ago, when I was a third-year undergraduate student, probably it was the first time where this conference was organized. And I was also a speaker at this conference. And for, well, many years, I have been a constant member of the jury. And so I'm always glad to be here, and thank you very much for organizing and for this work. That's very nice.
Well, thank you, Andrei, very much. Thank you. I'm very glad to see you today here. Thank you for coming. And also I'd like to thank all the participants of the conference for your work, for your ability to work, and for your desire. And I wish you luck.